Welcome back, Crammers, to question 2. A car park has a payment machine that allows a customer to pay for their parking. The cost of parking is displayed as a denary number on the screen on the payment machine. The cost of parking is stored in a 2-bit binary register. For the parking cost of 10.50, the first register stores the whole number and the second register stores the decimal, as seen here. Give the parking cost that will be displayed on the payment machine when the registers store this binary and this second binary. Now we can see here, let's start with register 1 over here. We have 0001 and we have 0001. Now moving right to left, we have 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, 2 to the power of 4, and so on. So we have 2 to the power of 0, so that there is 1, and we have 2 to the power of 4, which is 16. If we combine 16 and 1, we get the denary value of 17. So we know that register 1 is the whole number, so we can write here. And register 2 will give us our decimal. So again, we have 0100 and we have 0110. Now we have 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, 2 to the power of 4, 2 to the power of 5, 2 to the power of 6, so on and so forth. So 2 to the power of 6 is 64. 2 to the power of 2 is just 4, and 2 to the power of 1 is 2. If we combine all these values, we get 70. So our final parking cost displayed is 1770. The parking cost 1498 is displayed on the payment machine. Give the binary numbers that are stored in the register to display the parking cost. Again, register 1 is the whole number, so we simply have to subtract this. So we have 128, 64, 32, 16, 8, 4, 2, 1. This is simply our binary written as denary, and we can see that 14 is less than 16, so we have to subtract from 8. So we have 14 minus 8 gives us 6. Because we subtracted 8, we put 1 here, and we have 6 now. So 6 minus 4 gives us 2. And since we have 2 now, 2 minus 2 is equal to 0. So that is our final value. So here, our 8-bit for the first register is just 00001110. We can do this again for the second register, which is given here as a decimal, which is 98. Again, we can see that 98 is greater than 64. So we have 98 minus 64 gives us 34. Because we subtracted 64, we have to put 1 here. 34 minus 32 is just 2, so we subtract 2 here. And because we have 0 again, let's write this here for comprehension. 2 minus 2, that's 0. Because it's no more, we simply put 0 in all the remaining places. And that means our second register is 0110, 0010. The payment machine gives the customer a ticket when they have paid their parking cost. Each ticket has a 4-digit hexadecimal number that is stored as binary. The binary number is given and stored as the customer's ticket number. Give the hexadecimal ticket number that will be displayed in this customer's ticket, and we have to do this showing our working. We do this in 4, so here we have 4, then 4, then 4, and 4. Let's start off with this, okay? We have 1010. As I said before, we have 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, and 2 to the power of 3. 2 to the power of 3, so that's 2 times 2, 4. 4 times 2, that's 8. And we have 2 to the power of 1, which is just 2. And we get 10. Now remember, 1, 2, 3, 4, 5, 6, 7, 8, 9 is just given as 1, 2, 3, 4, 5, 6, 7, 8, 9. However, 10 is A, 11 is B, 12 is C, 13 is D, 14 is E, and 15 is F. So we know that the first value is 10, and 10 is just A. So we simply write here A as our first one. Now, moving on to the second one, we have 4 zeros. We have 0, 0, 0, 0. And since it's just 0, that means that our final answer is 0 because there are no ones we don't have to calculate. And 0 is just equal to 0. Now, our next 4 are given as 0, 0, 1, 1. So we have 2 to the power of 0, that's 1, and 2 to the power of 1 is 2. So we combine this, we get 3. And since 3 is less than 10, we just write it as 3 because 3 is equal to 3. Now our final 4 is 1, 1, 0, 1. So we have 2 to the power of 0, that's 1. 2 to the power of 1 is 0, so we don't write that down. 2 to the power of 2 is 4, and 2 to the power of 3 is 8. When we combine all of these, we have 12 plus 1, that is 13. And if we look here, 13 is given as D. So we simply write here D. So our answer here is A03D. Explain why data input into payment machine needs to be converted to binary. Now we know that binary can be either 1 or 0. It can only be yes or no. Did they pay or did they not? And that's what we write here. Binary can be written using logic gates. So we can write here, uses logic gates. And it only has 2 states. Only has 2 states. Did they pay or did they not pay? When a customer is leaving the car park, they arrive at a barrier, just the regular barrier that moves up or down. The customer needs to insert their ticket into a system at the barrier. The system needs to read the ticket number and then checks whether the parking cost has been paid for the car. The barrier is raised if it has been paid, and it does not raise if it has not been paid. The system uses a microprocessor. Describe the role of a microprocessor in a system and how it checks if the parking cost has been paid. So we can see that there are actually 4 different points given in the question, and there are only 4 points that we have to write. Firstly, it has to check our ticket against the system. Against the system. Using a database. The reason it uses a database here is because it has to check whether or not the ticket is actually genuine. The second point here is check if the ticket is listed as paid. And now for the final point, it says here the barrier is raised if it has been paid. So there are actually 2 points here. As said before, this is a binary system, so it can either be not paid or it can be paid. So if the data matches, raise the barrier. Raise the barrier. That means if they paid, let them leave. And the last one, if the data does not match, either it's a fake ticket or they did not pay, do not raise the barrier. Thanks for watching. Cram, then scram.